The James Webb Space Telescope, or JWST, is an outstanding scientific tool that is helping scientists understand more about the universe than was ever possible before with other observations. But now, the Supreme Observatory also seems to be putting astronomers into an unsettling predicament by constantly making unexpected discoveries. And the latest spectacle observed by James Webb revealed 100 Jupiter-sized objects that shouldn't exist, heralding the existence of a new astronomical category. Join us today as we dig deep into the JWST's new shocking discovery that will quite simply blow your mind. The next great era of astronomy truly began the morning of Christmas Day 2021. After nearly 3 decades of troubled development and $10 billion in spending, a pulse-pounding launch on Christmas Day in 2021, and a nail-biting half-year of delicate preparations in deep space, the James Webb Space Telescope at last delivered a complete set of first full-color images. President Joe Biden himself offered a sneak preview of the images from the White House, revealing what is destined to become the most iconic picture from the set. As President Biden said during the event, these images are going to remind the world that America can do big things, and remind the American people, especially our children, that there's nothing beyond our capacity. We can see possibilities no one has ever seen before. We can go places no one has ever been before. Constructed by NASA, as well as Europe's and Canada's space agencies, Webb is controversially named for a former NASA administrator, and it is the most powerful off-world observatory yet built. But for a time, the observatory was more of a cruel joke among astronomers. The technical demands of its development pushed the project so far over budget and behind schedule that many suspected it would never launch at all. But now it promises to revolutionize our understanding of the cosmos during a mission that could stretch into the 2040s. Each of the telescope's latest images has marshaled the might of at least one of Webb's 4 main instruments, as well as its giant 6.5-meter segmented primary mirror, composed of 18 coffee table-sized hexagonal slabs of gold-plated beryllium that folded together like a piece of origami to fit within a Ariane 5 rocket. Perched 1.5 million kilometers from Earth and shaded by a multi-layered sunshield as big as a tennis court, the telescope's kit is cooled close to the temperature of the vacuum of space. That deep freeze allows it to see, or rather feel, the infrared glow of far-flung galaxies, nearby planets, and everything in between. Even before official images were released, earlier pictures taken to guide Webb's complex deep space commissioning hinted at the observatory's stunning capabilities. Simple snapshots of a star obtained by the telescope's workhorse instrument, the Near-Infrared Camera, or NIRCam, also serendipitously included more than 1,000 photobombing background galaxies that would have been too faint to simply swim into view in any other observatory's optics. These and other preliminary tests, says NIRCam's principal investigator Marcia Rique of the University of Arizona, have shown that all of Webb's instruments are achieving even better sensitivities than we projected, and that the performance of its mirror is similarly exceeding expectations. With all these new images, Rique says, quote, "We are now seeing that the science returns are probably going to be even greater than we had dared to hope," end quote. Designed to showcase the breadth and depth of Webb's cosmic vision while also serving as enrapturing eye candy, these science images indeed do not disappoint. From our cosmic backyard in the solar system to distant galaxies near the dawn of time, NASA's James Webb Space Telescope has delivered on its promise of revealing the universe like never before. The global astronomy community has spent the past year or so excitedly poring over Webb's public data and getting a feel for how to work with it. Interestingly, beyond the stunning infrared images, what really has scientists excited are Webb's crisp spectra, the detailed information that can be gleaned from the light by the telescope's spectroscopic instruments. Webb's spectra have confirmed the distances of some of the farthest galaxies ever observed, and have discovered the earliest, most distant supermassive black holes. They have identified the compositions of planet atmospheres, or lack thereof, with more detail than ever before, and have narrowed down what kinds of atmospheres may exist on rocky exoplanets for the first time. They also have revealed the chemical makeup of stellar nurseries and photoplanetary disks, detecting water, organic carbon-containing molecules, and more. Already, Webb observations have resulted in hundreds of scientific papers answering long-standing questions and raising new ones to address the mysteries of the universe. The breadth of Webb's science is also apparent in its observations of the region of space we are most familiar with, our own solar system. Faint rings of gas giants appear out of the darkness, dotted by moons, while in the background Webb shows distant galaxies. By comparing directions of water and other molecules in our solar system with those found in the disks of other, much younger planetary systems, the James Webb Space Telescope is helping to build up clues about our own origins, how Earth became the ideal place for life as we know it. According to Webb's senior project scientist, Jane Rigby of NASA's Goddard Space Flight Center, with a year of science under our belts, we know exactly how powerful this telescope is, and have delivered a year of spectacular data and discovery, she said. Obviously, thanks to Webb's superior power, we have discovered a lot in this universe. From stars on the cusp of going supernova, cosmic tarantulas, and record-breaking space smoke, the James Webb Space Telescope has spotted many amazing sights in the distant cosmos. The images can be so in-depth that the results have been described as, quote, a new age of astronomy, end quote. But the James Webb Space Telescope continues to surprise us. And the latest spectacle observed by the JWST revealed dozens of planet-sized objects have been discovered in the Orion Nebula, heralding the existence of a new astronomical category. The free-floating entities have been named Jupiter Mass Binary Objects, or JUMBOs. The objects are too small to be stars, but also defy the conventional definition of a planet because they are not in orbit around a parent star. The discovery also appears to confound existing theories of star and planetary formation, which suggest it should not be possible to form Jupiter-sized objects through the process that gives rise to stars inside the clouds of dust and gas found in a nebula. Professor Mark McCaughrean, a senior advisor for space and exploration at the European Space Agency, or ESA, said the observations were inspired after data from ground-based telescopes hinted at the existence of the mysterious class of objects. We were looking for these very small objects, and we find them, the professor said. We find them down as small as 1 Jupiter mass, even half a Jupiter mass, floating freely, not attached to a star, he said. Physics says you can't even make objects that small. We wanted to see, can we break physics? And I think we have, which is good, he said. The large, hot, gassy objects appear to be planet-like in their composition, like analysis revealing steam and methane in their atmospheres, but they are not technically planets. The team settled on the name Jupiter Mass Binary Objects, or JUMBO, because out of the hundreds of planet-like objects identified, dozens came in pairs. Like McCaughrean explained, most of us don't have time to get wrapped up in this debate about what is a planet and what isn't a planet. It's like my cat is a Chihuahua Mass pet, but it's not a Chihuahua, it's a cat. The JUMBOs are about 1 million years old, babies in astronomical terms, and have inferral surface temperatures of roughly 1,000 degrees Celsius. Without a host star, though, they will rapidly cool and will briefly feature temperatures in the range of habitability before becoming incredibly cold. However, as gas giants, their surfaces would not harbor liquid water, even during their brief temperature window, meaning they are not likely to be strong contenders for hosting alien life. The observations focus on the Orion Nebula, which can be seen with the naked eye as the fuzzy middle star in the sword of the Orion constellation. At 1,344 light-years away, it is the closest region of massive star formation to Earth, and in the latest images, It appears as a celestial masterpiece, with roiling clouds of dust and gas, explosions and star beams. Stars form when the dust and gas clouds in the nebula cool, progressively fragment, and eventually collapse under their own gravity. The smallest stars are about 80 Jupiter masses, below which the core is not dense enough to fuse hydrogen, but smaller objects can coalesce through the same process, including dimly glowing brown dwarfs, sometimes called failed stars, and below about 13 Jupiter masses, planetary mass objects. But theoretical predictions suggest that the lower boundary for an object forming through a star-like gravitational collapse is about 3 to 7 Jupiter masses. Smaller free-ranging objects have occasionally been sighted, but it was unclear whether they had formed in situ or had been ejected from a planetary disk around another star. The latest observations are more challenging to explain because, out of the hundreds of roughly Jupiter-sized objects found, dozens are in binary pairs. How can you throw two things out of a star's orbit or in a chaotic interaction and get them to stick back together again? Asked McCogran. These findings are published as a preprint, but are yet to be peer-reviewed. Professor Matthew Bate, the head of astrophysics at the University of Exeter, who was not involved in the research, said, "I don't know how to explain the large numbers of objects they've seen. It seems we're missing something in all of the theories we've got so far. It seems that there's a mechanism that's forming these objects that we haven't thought of yet." It's pretty rare that this kind of discovery is made, Bates said. In the last decade, a lot of us thought we understood star formation pretty well. So this is really a very, very surprising result, and we're going to learn a lot from it, he said. Professor Anthony Whitworth, an astrophysicist at Cardiff University, described the observations as, quote, "an amazing result," end quote. The binary objects could have formed within a disk and then been kicked out as a pair, he speculated. This would require interactions with other stars in the dense Orion star field, he said. All possible in principle, and lots to ponder, Whitworth said. The James Webb Space Telescope is quite simply providing scientists with an unprecedented view of the universe, allowing scientists to peer through obscuring clouds of gas and dust. Interestingly, the observation is on track to finding alien life in the universe. According to scientists, it's only a matter of time. The early year marked the very first time the James Webb captured one of those planets within our universe. Named LHS 475b, this planet happens to be the most identical in size to Earth, with its radius determined to be about 99% as large as our home planets, although it's in a fairly close, tight orbit around its parent star. That star is relatively cool, an old, stable red dwarf star. As the planet, serendipitously aligned with its parent star from our perspective, transited across the face of its star, JWST got a chance to observe it, using the technique of transit spectroscopy to measure its atmospheric contents. But what it found was instead a disappointment, consistent with there being no atmosphere at all. It's a remarkable step forward for science, but also one that suggests the JWST's nightmare scenario for exoplanet discovery might come true. But hold on, let's back up for a minute and talk about what a dream scenario for JWST would be. Out there in the universe, there are more planets than stars, with almost every star that forms late enough in the game, from material that's been sufficiently enriched by prior generations of stars, containing multiple planets of various sizes and orbital distances around it. When those planets happen to orbit around their stars, in an orientation where the planet passes directly in front of the star, from our perspective, a portion of the star's light is blocked, causing the star to temporarily become dimmer during these planetary transits. But while the solid disk of the planet simply obscures the starlight that strikes it, planets can also possess atmospheres, partially opaque but partially transparent to the incident starlight. As the starlight filters through the planetary atmosphere, the molecules and atoms present absorb light in particular wavelengths, the wavelengths that excite the electrons within those atoms and molecules. As a result, when we break up the light we receive spectroscopically into its individual wavelengths, we can detect absorption lines, teaching us what's present in the atmosphere thanks to the technique of transit spectroscopy. In addition to the known, confirmed exoplanets that are out there, missions that measure planetary transits like Kepler, K2, and TESS also yield thousands of exoplanet candidates, where a one-time or even periodic dimming is seen, but where the signal hasn't become robust enough to declare a definitive, confirmed detection. One of those planet candidates was known as TOI-910.01, meaning that an event consistent with a transit was seen by the TESS satellite, but that what TESS had seen wasn't sufficient to declare a true discovery. It still might have been a false positive. That's when another observatory has a chance to come in and look for a definitive signal. For the very first time, JWST was that observatory in this case, examining the parent star, known either as TOI-910 from its TESS number, or LHS-475, its more common name, and detecting that critical dimming effect. Even though only about 0.1% of the parent star's light was blocked, JWST was able to detect the signal unambiguously, detecting two transits lasting about 40 minutes long, observing the clear dip in flux with a series of observations that broke the data up into about 9-second chunks. It's really an unambiguous signal. There's no doubt about the planet is there. This marks the very first exoplanet officially discovered by JWST, and the stats on what it discovered truly do showcase the power of JWST to do a whole lot more planet finding and planet characterization in the future. The new exoplanet, officially named LHS-475b, is 99% the radius of Earth, with just 0.5% uncertainty, located 40.7 light-years away, placing it relatively close by, orbiting around a cool red star that's middle-aged, non-flaring and stable in its brightness, and capable of having transit spectroscopy performing on it by JWST's near-spec instrument. Being able to perform transit spectroscopy leads to a series of tantalizing possibilities. As light filters through a ring-like region surrounding the planet, it can stimulate both emission and absorption features dependent on what sorts of material is present and what its properties are. Venus, Earth, Titan, and Mars, were they to transit across the face of a star like LHS-475, would all lead to different signals, all of which in principle would be revealed to a sensitive enough observatory. A Venusian atmosphere would be very rich in clouds, which would serve as an extreme opaque medium, perhaps indistinguishable from a solid planet. However, the components of atmosphere, where there are either breaks in the clouds or incomplete cover, or that are above the clouds, would still lead to interesting signals. Earth's signal would display a reddening as well as oxygen, nitrogen, and water vapor signatures, while Titan's methane and hazes would be extremely easy to see. Mars, however, with a thin carbon dioxide atmosphere and a tiny bit of nitrogen, would create a very small signal, requiring a very large amount of observing time and a high signal-to-noise ratio. But if the planet that transited across the star was instead like the Moon or Mercury, with no atmosphere at all, performing transit spectroscopy would lead to the most boring spectrum of all, one that was entirely flat. And when the spectrum of LHS-475b was taken by JWST's near-spec instrument, that's precisely what it observed, a spectrum that was 100% consistent with being purely flat, with many possible other outcomes, like a hydrogen-rich or nitrogen-rich or even a methane-rich atmosphere all being disfavored by the data. Despite our hopes that the Earth-sized planets we'd be finding with JWST would possess a rich and diverse set of atmospheres, this very first one delivered exactly the opposite result. The same result you'd get if this were a completely atmosphere-free world, or just a sphere of solid material orbiting around the star LHS-475. The observations rule out a wide variety of plausible atmospheres for what could be around this planet. The only realistic atmosphere that could remain is a Mars-like one, thin and very dominated by carbon dioxide. Technically, this is a very nice result, though. Prior to JWST, it was only the large, giant planets, the ones practically guaranteed to have large amounts of gas around them, that it was possible to perform transit spectroscopy on. The incredible pristine properties of JWST allowed us to go all the way from Jupiter-sized worlds down to Earth-sized worlds in our quest to measure the contents of exoplanet atmospheres, and to do it successfully. It's neither the fault of the telescope nor of the researchers that the first JWST discovered planet just didn't happen to have an atmosphere. There are a few possibilities as to why this could be, and while some of the possibilities are rather mundane, the most likely one might indeed be the nightmare scenario. The dream scenario, however, that practically all Earth-sized planets have rich, diverse atmospheres, like the two Earth-sized worlds in our own solar system, Venus and Earth, do, is antithetical to this first result. The most optimistic possibility remaining, that's worth consideration, is that this newly discovered planet, LHS 475b, really does possess an atmosphere, and that JWST will be able to detect it. The spectrum it was able to obtain was only possible to acquire during the brief moments that the planet transited its star, and with two transits of about 40 minutes, that simply isn't very much time to acquire the needed signal. In the acquisition of this data, JWST hasn't yet seen its noise floor appear, so it's plausible that acquiring more data from subsequently observed transits could yet reveal an atmosphere, and even one that was almost exclusively carbon dioxide, would be revolutionary in informing our understanding of planets. Less optimistically, it could be the case that this particular exoplanet doesn't have an atmosphere, but that many or even most of the Earth-sized worlds out there, the majority of which are going to be found around low-mass red dwarf stars, actually do. In this scenario, it's only for reasons similar to why Mercury has no atmosphere that LHS 475b has no atmosphere, because the planet is too close to its parent star and too low in mass combined to have retained the atmosphere after billions of years of being bombarded by radiation and wind particles from the starred orbits. We have every reason to expect that Earth-sized planets around Sun-like stars should be able to generate and maintain atmospheres, but there's a huge question of whether this is also possible around red dwarf stars. Red dwarf stars, or M-class stars that are generally lower than 40% the mass of the Sun, tend to rotate rapidly, flare quickly, and would inevitably tidally lock any planets that would be located within or interior to the star's so-called habitable zone. These are the majority of stars in the universe that possess the majority of Earth-sized planets in the galaxy and universe, and these are really harsh conditions. That's why the nightmare scenario is, unfortunately, so frighteningly likely. JWST, as wonderful as it is, still has a limited set of capabilities. It's capable of detecting Earth-sized planets that transit across the face of small stars like red dwarfs, because the planet blocks a significant fraction of the star's light, something like 0.1%. But if the star is bigger, and Sun-like stars are larger, then the fraction of light that an Earth-sized planet will block is much lower, and JWST won't be able to resolve planets that block something like less than 0.01% of their star's light or less. Earth-sized planets around Sun-sized stars are invisible to JWST. In this nightmare scenario, JWST would never successfully detect an Earth-sized planet's atmosphere. Regardless, noting that it's always tough to draw general conclusions when you've only looked at one object, and LHS 475b is just the first Earth-sized planet discovered and measured with transit spectroscopy using JWST's NIRSPEC instrument. Webb will make more and more stunning observations, that's for sure, and it all depends on what the universe delivers to us, something we won't know for sure until we have much larger sets of transit spectroscopy data. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content like this and to always improve. As always, thanks for watching, and we'll see you next time.